Hello and welcome to Chapter 4 lecture on forces and Newton's laws of motion. So Newton was a uh, physicist who is kind of the physicist who invented basically everything that we use for physics up until through classical mechanics and up until Einstein really threw a wrench into everything in 1905. So he is most famous for coming up with three laws of motion that are still used to this day and are still the most fundamental ways that we understand forces. So what is a force? Just a second. A force is defined as being something that causes motion. So it's a push or a pull. Uh, and then dynamics is the study of how forces uh, cause motion. And then they add together. So when you push five newtons, which is the unit of force to the right, and you push 3 newton, somebody else pushes with 3 newtons, which is the unit of force again, to the left. The net force is going to be 2 newtons to the right because one of them is the 5 newtons is going to cancel out the three of the newtons, and then there's going to be a net force of 2 newtons. So they add together, and they add together as vectors. So there are a number of different forces, and they can generally be broken down into contact and non-contact forces. So contacts are forces like tension, normal force, friction. We'll get more into what those are in the future. But tension is just how hard a string or cord is pulling on something. And then another contact force would be if you were physically pushing an object, while as a non-contact force is something like gravity or electromagnetism, or the nuclear forces, which is when you are not directly pushing an object, but there's still a push or a pull, such as when you are out in space, when you are the moon, you're not touching the Earth, but you're still being pulled towards the Earth by gravity. And a way that we come up with to describe these forces is something called a free body diagram, where we represent the object being acted upon as a single point and show external forces as vectors, which are arrows indicating the magnitude and direction of the force. And then from looking at these vectors, we can tell which way the net force is going to go. So in this case, we have tension pulling up and weight, which is the force due to gravity, pulling down. And because the object is not moving, or it's just hanging from a rope and not accelerating downwards, then tension would be equal to the weight of the object. And then another thing to notice about free body diagrams is that only external forces cause motions. That's means that only forces that aren't internal to the system that you're looking at cause motion. So, for example, in your body, in this weight, there are a ton of different forces, a ton of different electromagnetic and gravitational forces uh, causing uh, causing the weight to stay in a steady form and to be a solid object. But we don't talk about any of those forces when we talk about uh, the net force on an object, because it's going to turn out by Newton's third law that they all cancel out, and more on that later. So Newton's first law is that a body at rest tends to remain at rest, and a body in motion tends to remain at motion at a constant velocity unless acted upon by a net external force. And then constant velocity is just going straight forward in a straight line with a constant speed, if you'll remember that. So this is kind of unintuitive, uh, or at least it was uh, 2 or 3 thousand years ago when Aristotle, I believe, was the one who came up with the idea that all objects want to return to their natural state, which is for earth elements such as like rocks, just in the center, or they want to return as close to the earth as possible and not moving. So Aristotle made the argument that all objects are going to slow down and return to their net state of zero velocity unless acted upon by an outside force, whereas Newton made the argument that uh, they would keep going forever unless acted upon by an outside force. And the one who is right about this is Newton. So if you look at the diagram on the right, or on the bottom right, what you'll see is that there is a net force acting as you uh, go across even an icy pond, but most especially if you go across rough surface. It's something called friction, which is a force that always kinetic friction always opposes the direction of motion. It always opposes and points in the opposite direction of the velocity, and it causes, because it's a net force in the opposite direction of velocity, it causes the velocity to slow down uh, and come to a rest. Now, we uh, determined that a net force is required to cause a change in motion. That's what Newton's first law is, but how does that change in motion uh, apply? Is it proportional to velocity? Is it proportional to acceleration? Is it just proportional to the displacement? So what Newton's second law is that the force net is equal to mass times acceleration, which means that the acceleration is proportional to the force moving on a system. So a uh, as you move an object forward with a constant force, it's going to accelerate constantly. And if you have an object that's moving with a non-constant force, then the acceleration is going to be proportional to this force, non-constant force that's acting on the system. So it's proportional to acceleration is proportional to force, and then force is equal to mass times acceleration, where mass is just a quantity telling us how hard it is to move something. So the more mass you have, the harder it is to move something. So if you put all of your effort into pushing a block with a mass of 10 kilograms, then that is going to accelerate twice as much as if you had pushed a block with 20 kilograms, because the more mass makes it harder to accelerate, and it does that directly proportional if you know how that works. So basically, another way that you can put F equals ma is that acceleration is equal to, just a second, you can put that acceleration is equal to F net over m, which means that the acceleration, as m goes up and F remains constant, then acceleration goes down. And that's just the proportionality between mass and acceleration. So what does it mean when we say that uh, it's the mass of a system? So what is mass? Mass is related to weight. So weight is equal to m times some constant called g on the surface of the Earth. So something with twice as much mass is going to have twice as much weight, but mass is constant no matter where you are in the universe. So if you're on Mars and you have a 10 kilogram mass, then you're carrying a 10 kilogram mass, then it's going to be also be 10 kilograms on Earth. But if you're the weight, how much force is being exerted by the mass is going to be less on Mars than it is on Earth. So object on Mars is going to weigh less than it does on Earth, even though they have the same mass. And the mass is kind of just a quantity telling us how much of how many atoms there are in something and how many and what type of atoms are making it up. So just a second. Oh, that turns out to be the end of the presentation. No, that definitely shouldn't be. There we go. We didn't even get to Newton's third law, so that is definitely not the end of the presentation. So Newton's third law is the last of the three laws of motion, and states that when an object exerts a force on a second object, the first object experiences a force in equal magnitude but opposite direction of the force that it exerts. So, for example, when you press against a tree or you punch a tree, the tree's not going to do anything back to you. It's not going to make a motion or try to punch you back. But when you do that, the force that you exert on the tree is going to cause there to be an opposite force pointing in the same direction, or in pointing in a force pointing in the opposite direction with the equal magnitude, canceling these out, or canceling the force that you applied out. So if you hit a tree with a force of 10 newtons, then the tree is going to hit you with a force of 10 newtons in the opposite direction. So this is why we can ignore internal forces in our free body diagrams. So I've been saying that you only need to worry about the net force and the external forces that are acting on an object. So the forces that come from outside the object acting on the object, such as gravity or friction or tension, caused by a rope or the ground or the earth, in opposite order. And the reason we can ignore all of the other forces that are acting on it, like the electromagnetic forces that keep the object from falling apart by pulling them together, is that each of them has an opposite force, an force opposite in magnitude that's acting on the other atom in this object. And what ends up happening is that all of those forces cancel out. So you only have to worry, when you look at the net force, at the total force, you only have to worry about the force from outside the system, because everything inside the system is going to cancel out. And it gives rise to something that we call normal force, which is just the force that when you're in contact with another object, it's going to push back at you with however much force you apply, it's going to push back at you with that same amount of force. And it's the force, normal force is the force that keeps us from falling through the ground, because we're being pulled by gravity all the time, but the floor pushes back up onto us. And that normal force keeps us in equilibrium and keeps us from falling through the ground. And then that is actually the end of the presentation. Thank you very much, and I'll see you later.